All right, 4Cs, this is a lesson on a simple machine called the screw. Yesterday, we talked about the inclined plane. You saw a short video, a Eureka video, that talked about a screw and that how a screw is simply an inclined plane that's wrapped around or spirals around a cylinder or something like that, just like that windy mountain road you saw in the Eureka video. So just a few simple equations and diagrams will help us through these questions, all right? So away we go. A screw is basically an inclined plane that's been wrapped around a cylinder, as I said. There's a simple diagram that you can use. The turning radius of the screw is right at the top there. You can see it listed R, all right? That is basically a part of your effort radius. For one round, the length of the inclined plane is the circumference of the screw, because you have to think that this is like an inclined plane except it goes all the way around. So we have to calculate the circumference of the screw to know basically the length of the ramp. So instead of L, like we had in the ramp equation, we have circumference, which is 2 pi r. The height of the ramp is the distance between two threads, like right in there. That's h, that's height, all right? Because if you're calculating the length as one circumference, well, how high do you go in one circumference? Well, it's going to be just the distance between threads, okay? And that's called the pitch of the screw. There's the ramp equation that we used yesterday, and it's load force times height equals effort force times length of ramp. But now we're replacing length with circumference, which is 2 pi r, and we're replacing height with pitch, and we're replacing length with 2 pi r, rather. Let me just move this out of the way. And there we go. That is your screw equation. You can see that length's been replaced by 2 pi r, and you can see that height's replaced by pitch. Load force and effort force remain the same. We don't have to make a modification to our actual mechanical advantage. Like I said before, it's the same for every single machine in that it's load force divided by effort force. Same for all machines. But the IMA is equal to 2 pi r over pitch. Remember, for the ramp, the IMA was equal to length over height. Real simple. But now we're replacing length with 2 pi r, the circumference, replacing height with the pitch. Example number 1, a 250 Newton beam is being lifted into place with a screw jack having 12 threads and 5 centimeters. If the handle has a radius of 22 centimeters, what effort must be applied? So it's going to be hard for me to draw on the smartboard, but I'll try and draw you a picture here of what's happening. All right, so here we've got our turning radius of r, which is from there to there. So we'll be able to calculate 2 pi r fairly easily. But it's a little trickier to calculate the pitch in this case, because all it says is there's 12 threads and 5 centimeters. So if we go 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12. Now, when you're doing these on a test or assignment, you don't have to draw this picture. I'm just trying to explain to you how to get pitch when you're given something like 12 threads in 5 centimeters. So basically, you just take the distance, the 5 centimeters. So how many centimeters per thread if there's 5 centimeters and 12 threads, all right? So the pitch is simply going to be equal to 5 centimeters divided by 12 threads. And that's going to be equal to 0 decimal. I don't even have a calculator set to go here. So I get out the Casio 991, I go 5 divided by 12, It gives me 0.42, and that's centimeters. All right, there is your pitch. All right, so we've got pitch, we've got R, we've got the weight of the beam. That, of course, is going to be your load force. And now we can just apply that equation. All right, this one is a little trickier to use mathematically because there's these extra, they're not variables, but there's extra coefficients, 2 and pi. So let me show you how that works. So I'm going to go load force times pitch equals effort force times 2 pi and R. The values we've got here are 250 newtons times the pitch, which is 0.42 centimeters, equals the effort force, that's what the question says to find, times 2 pi and 22 centimeters. All I got to do is multiply the two that are together, the 250 times the 0.42, and divide by the others. Just make sure you have the brackets in that, okay? Because you're going to have to type into your calculator 250 times 0.42 divided by, and make sure you use brackets, 2 times pi times 22. All right? Then you hit equals. That'll be your effort force. What's it going to be in this case? 250.42 divided by bracket, 2 times pi, find your pi button, or type in 3.14 times 22. Gives me 0.76 newtons. As you can see, this type of screw has a really, really big mechanical advantage, right? You're going to see this come up, this whole, how it's 12 threads and 5 centimeters, in I think the first word problem on your assignment, okay? It says something like there's 8 threads in an inch or something like that. So 1 inch divided by 8 threads will give you the pitch. It'll give you the distance between any 2 adjacent threads, all right? So just be prepared for that. We'll try one more example here. A bolt with a pitch of 0.15 is being tightened with a wrench that's 25 centimeters long. That's going to be your turning radius. What is the mechanical advantage? Well, that's fairly simple. We've just got pitch, which is equal to 0.15 centimeters. It says we've got a radius that's 25 centimeters long. What's the mechanical advantage? In this case, we'll probably be finding IMA. Why? Because we've got distances instead of forces. AMA is FL divided by FE, and IMA is 2 pi R over pitch. 2 pi R divided by pitch. In this case, that's going to be 2 pi times 25 centimeters divided by 0.15. And again, this example is going to illustrate that you get huge mechanical advantages out of the simple screw. 2 times pi times 25 divided by 0.15, it equals, and I got 1,047. 1047. No units on it because the centimeters cancel the centimeters, and nothing else has units on it. So that's a huge mechanical advantage. When you compare that to like what we were getting out of the ramps, you know, you typically get a mechanical advantage of 2, 3, or 4. That's about all you can really get feasibly in the real world. But with the screw, you can wrap that ramp around the cylinder and get quite a large mechanical advantage out of it. And that's the way that works. So what I want you to do now is complete yesterday's work from the ramp. I want you to complete the handout for today, which is on the screw. The math, like I said, is a little bit trickier because of that 2 pi R. You know, you have to make sure to divide it out. Like if you're trying to solve for r, for example, there's that 2 pi you got to worry about. It's not as simple as before where you just multiply the 2 and divide by the other one. You got to multiply the 2 and divide by the other one and divide by 2 pi in some cases. So be careful with that. Good luck. We're going to do a lab tomorrow on the ramp. All right, mechanical advantage and percent efficiencies involving a ramp. Compare that to the efficiencies with a lever. And yeah, good luck.